All right, welcome to day two of content. The first two meetings, and what I mean by that is, the first class, second class, the videos for those that are loaded into the modules are mostly content in terms of theory. They're mostly theory. So in the first academic adventure, you'll have a lot of multiple choice questions based on these first 2 days of content, because it's so content heavy. Today we will go, in a later video, I will go over the first problem that we'll have to be able to do, that you will get, absolutely will get on your first academic adventure. We'll go over that for you. But it's very, very, very theory-oriented for the first several videos, as we have to learn to talk the talk before we can walk the walk. And today's another one of those days. So if you go and get your topics covered for today, you will see, starts with phase changes, and we will dive right into that. Now, phases of matter. Now, we've actually gone over the phases of matter because we did a review of the liquids, solids, and gases. There's a fourth phase of matter, of plasma, but we don't deal with that here in general chemistry. So our 3 phases of matter, liquid, solid, gases. We went over what they are. Now, to change phases. Now, you've heard of these words. You absolutely have. You've heard of boiling and freezing and melting and condensation as well. You might not have known that there are words that are the same temperature occurrence. In other words, let's say that we have a melting point. And you know the melting point of ice. You know what it is. 0 degrees Celsius, and that's also the freezing point of ice. Now, sometimes I'm surprised that people don't know that they occur at the same temperature. But you might not have thought of that. You might go, oh yeah, I guess they do. Anyway, that's kind of weird, right? No, not really. Something can melt and freeze, and that occurs at the exact same temperature. Well, how can it occur at the same temperature? Like if it's 0 degrees Celsius, would water be solid, or would it be liquid? Would it be melting, or would it be freezing? The answer is yes. Exactly. An ice water bath is at 0 degrees, and what you have is you have both phases. You have the freezing point phase and the melting point phase. So they occur at the same temperature. Now, whether or not something is going to freeze, so if you have ice water, will it all turn to ice, or will it all turn to water? Now, if you have it out at room temperature, you know the answer to that. Stick around for a little while. Watch what happens. Watching, eventually the ice melts and turns to water. Well, that's because energy is going into the system. So what happens at this point, melting and freezing, so with water at 0 degrees, is will the ice melt or will it freeze? The answer is, what's energy doing? Is energy going into the system? If energy is going in, it's going to melt. If energy is going out of the system, we're taking energy out, taking heat out of the system, going to freeze at 0. So it depends on what's happening. So your ice water bath at room temperature, well, room temperature is warm, so energy from the room will go into the system, it'll melt. So eventually you'll get just water. Okay, but they do occur at the same temperature, and the other one that occurs at the same temperature is boiling and condensation. Boiling point, we know what that is. Water boils at 100 degrees Celsius or 212 Fahrenheit. But also condenses at that temperature. Now, it can condense at lower temperatures than that, absolutely. But when it occurs at the boiling point, so when we get water, I use water as an example. All things have melting points and freezing points. It's not just water. For example, where'd my stapler go? I don't need a stapler. I can use this pair of scissors. Okay, that is stainless steel. That is solid, frozen stainless steel. Now, most people go, wait a minute, frozen? It's got to be cold. Okay, let it go, let it go. La 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 la. Overrated movie. Okay, in my humble opinion, overrated. So here is the frozen steel. Now, it's not cold. Frozen doesn't mean cold. We associate it with cold because when we talk about freezing, we're talking about water. That's our typical everyday experience. But this is certainly frozen, solid steel. So when you have something which is frozen, it means in the solid state. It doesn't have to be cold or hot. It just depends on what the temperature of the thing is. If you wanted to freeze steel, okay, solidify steel, okay, that occurs at a much higher temperature than 100 degrees Celsius even, which is the boiling point of water. So that freezing point, the melting point occurs at a high temperature. And the freezing point of water is at 0, while the freezing point of steel is a lot higher than that. Okay, so I mean, a lot of times we think of these words and we think our everyday experiences are based upon water and weather, because weather is water-based, of course. All right, moving on. This is just a blah, 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 right? But condensation occurs at 100 degrees as well. If energy is going out of the system, if you had vapor at 100 degrees Celsius, water vapor at 100 degrees, so you're boiling water and it's turning to vapor, well, that quickly condenses, doesn't it? Yeah, you boil a pot of water on the stove and you're going to see like liquid over things, on things that are up and above the boiling water. Well, what happened? Well, that boiling water went out and hit something which is cooler, took energy from that hot steam and condensed it back into liquid water. So this also occurs at the same temperature, which for water is 100 degrees Celsius. Okay, so the terms we know are boiling and freezing. So melting, turn to a liquid, freezing, turn to a solid, boiling, turn to a gas, condensing, turn back to a liquid. Okay, you can certainly get condensation occurring. You can have water vapor in the air in a hot, humid summer day. There's a lot of water vapor in the air. And if you get your nice ice cold glass of lemonade, set it down, well, you're going to very quickly see condensation on the outside. Well, what happened? Well, the water vapor hits the cold glass and they stick together, some water vapor, and they condense and form droplets of water. So condensation can occur below the boiling point. It can occur below the boiling point. And so can evaporation. And that's why I want to go into the distinction that if I were to ask you, define evaporation. Well, many of you will probably say, well, that's when water kind of evaporates. Okay, well, that's not answering the question. It turns to a vapor, evaporates. So water turns to a vapor. But the difference between boiling and evaporation, well, they both have a similarity. At evaporation, when water evaporates or is boiling, it's water is turning to a gas. That's what they have in common. So in common, well, of course, I'm using water. I'm saying water, but this is anything. It doesn't have to be water. It can be, for example, picture alcohol. You know alcohol evaporates quite rapidly, don't you? Yes, you do. You take alcohol, pour it onto the table, and rubbing alcohol, and watch what happens. And you put it on your skin feels cool. Why is that? Because it draws the energy from your skin and evaporates very rapidly. And your skin feels cool because it lost all that energy that went into the evaporation of the water. So when something evaporates, it turns to a vapor. Okay? It turns to gas. And in alcohol does that very quickly as opposed to water. Because remember the last time that we did videos in the last unit? What's the word? Here's an I. Because water has strong intermolecular forces, yes, those hydrogen bonds which keep it together longer. Alcohol doesn't have those. It has intermolecular forces, but they're weaker, and so it evaporates quicker. Okay, so it turns into a vapor. So let me just put, I'll take the word water off because it doesn't have to be water. And we'll put turns to anything to a gas. Okay, so that's a similarity between boiling and evaporation. Two differences, though. Boiling occurs throughout the entire liquid. It's good, clean, family fun. Go get a pot of water, bring everybody together, watch it boil. It's fun. Well, it's fun until you hear the screaming molecules. Remember? Yeah, they scream. You listen, those molecules are screaming. No. They don't want to separate. But this occurs throughout the whole liquid. Watch the water boil. Where is it boiling? Where do you see bubbles forming? Just at the top. No, you see them throughout the whole thing. They form all over the way. They form at the bottom and they'll rise to the top, so they will form throughout the whole thing. Turning to a gas throughout the whole liquid is what boiling happens. This only happens at the surface. Only at the surface. Throughout whole liquid, surface only. And not only does this only occur at the surface, it can occur below the boiling point. Well, if it's going to be boiling, it's got to occur at the boiling point. Say, you get it. Evaporation occurs below the boiling point. You know this is true after a rainstorm. You know, you watch puddles of water, they stick around forever. I mean, do they just start bubbling up through you? Do you see that? No, you don't see that. They don't boil. They just seem to get lower and lower and lower in volume until eventually the puddle is gone because it's evaporating. It's not 100 degrees Celsius outside after a rainstorm. Boy, would that be a bad day. All right, you would not be happy on that day. It'd be really hot. And so the liquid goes away. It doesn't do it throughout the whole liquid. It occurs at the surface and below the boiling temperature. So water can evaporate at 40 degrees. 40 degrees, well, I was gonna say Fahrenheit, you know, on a cool day water evaporates. But it occurs at the surface. It happens much faster if sun comes out. Why is that? If the sun's out, that radiant energy will strike the surface of that water, and that'll cause those molecules to pick up energy and vibrate faster. And eventually, the higher energetic molecules at the surface go, whoa, and fly off. All right? Throughout the whole liquid, at the boiling point. At the surface, below the boiling point. Now, evaporation occurs at the boiling point as well, but it can occur below the boiling point. So there's a difference between these terms, and we got to know those differences. Okay, people? Okay. All right, let's see, moving on here. Now I'm keeping up with the sheet for all of you. You know, some people out there are very anal retentive. They go, no, make sure you go in order. You must be in order. Thank you. Okay. So in order, I'm following down here. We're going to do vapor pressure and equilibrium vapor pressure. Okay. Vapor pressure. What's vapor pressure? Well, think of the word. The two words, vapor and pressure. Vapor gas is going to cause pressure. Now, it's going to cause pressure. Let's think of a closed container. So let's say we have a jar that has some water in it, and it has a lid on it. Put a lid on it, boy. All right, put a lid on it. That means be quiet. That's what my dad used to say to me. Put a lid on it, boy. Okay, Dad. Where was I? Sorry, childhood flashback. Oh, yeah. So we have a jar. It's closed. And because if it's not closed, we're not going to be able to get the idea on what vapor pressure is. So we have water, which we know can vaporize, can turn to a gas. Now, if water is in a jar, it will still evaporate. It's not going to boil unless we've got, some kind of energy source down here, but it's just sitting out here. Just sitting out, minding its own business, chilling like a villain. Okay, just hanging out. Just room temperature, hanging out. Well, what's going to happen? Some of the water molecules at the surface are going to, gain some energy. And when they do that from sources inside the jar, they get random gainings of energy. They'll boop, go into the vapor phase. So we will get some of this water to vaporize. So here's my little gas particles of water vapor inside the jar. That'll happen. And what will also happen is occasionally some of these water molecules, and they're moving all over the place, and they're striking the walls of the container and the lid of the container. That's called pressure. When something smacks into something and puts a force on it, that's force per unit of area. It's called pressure. So these vapor molecules, vapor molecules of water will cause pressure inside. Hence, vapor pressure. Yeah, we've got vapor, it's hitting the container and causing pressure. Okay, that's relatively easy. Now, what's equilibrium vapor pressure is this. Well, equilibrium means things happening in one direction are equal to things happening in the other direction. If you sit outside of a Walmart and just watch people go in and out, it's going to be kind of creepy if anybody notices you doing this, and security might be a little upset about it and kind of wonder what the heck you're doing. But just try this at home. Okay, just go ahead, go to a Walmart and just watch people going in and out of the store. Okay? And keep count of how many people, in maybe in an hour, in a particular amount of time, come in and go out of Walmart. Early in the morning, you're going to get more people going into Walmart as soon as the store opens than are coming out because nobody's in the store. So more people go in and nobody's coming out. That's not equilibrium. When the store is closing at night, attention shoppers, bring your purchases for checkout because the store is closing in 5 minutes. Okay, well, you're not going to get anybody going into the store at that point because it's closing and everybody's going to be coming out. That's not equilibrium. Try it at noon. Check it for an hour. Just watch people for an hour. How many go in? How many go out? I bet it's going to be pretty darn close to the same amount go in, same amount go out. That's equilibrium. So when you have as many people going in as are going out over a period of time, equilibrium. Okay, same thing here. Let's go back to our chemistry and get away from Walmart. People think you're a creeper. I've done it. Trust me, they do. They think you're creepy. So you have molecules coming out of liquid to vapor, and then some of those molecules crash into the surface of the water and go back into vapor. So equilibrium is when you have as many going into vapor as are coming out of vapor, going back into liquid. That occurs after a certain amount of time. Now, if I had just put the jar on the water, there'll be no vapor in there. And it would be like Walmart opening in the morning, right? Everybody's going into Walmart. So as soon as I put the jar on, I'm only going to have molecules going into the vapor phase. So that's not equilibrium, but give it a little time. We have molecules going into vapor and molecules coming out of vapor, equilibrium. Well, what would happen? That would be the equilibrium vapor pressure. So if you were to take a pressure vapor reading, let's say we had a manometer is something that measures gas pressure, we could get what the pressure is inside that container. And if it's at room temperature, we could very quickly, actually, you don't even need a manometer, we could figure out what vapor pressure is on a chart. Boop, 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 boop. Okay, that's the pressure. What happens if the temperature was up in the room? Well, let's say it's like, it was 20 degrees, but the air conditioning breaks, and it's like a mid-July, hot, humid summer day out, like 30 degrees Celsius, from 20 degrees, normal room temperature, 30 degrees, whoa, hot, hot, hot. What happens to the vapor pressure? You know. Yes, you do. You know. It becomes more humid outside because hot air can hold more water vapor. Yes, it can. Hot air, you know this is true. It's not humid. You don't even get a humid day in the winter. It's too cold to have a humid day in the winter. You get them in the summer when it's hot. So if it's hot outside, we can get more water vapor. It's more humid. And the vapor pressure will go up, yes. We'll get more of these water molecules going into the vapor phase, higher vapor pressure at higher temperature. So the relationship for pressure, for vapor pressure, and you know this from gas laws, you do know this from gas laws, that at higher temperature, we have higher pressures. We'll have higher vapor pressure at higher temperatures. All right, so pressure and the temperature are directly related to each other. You increase the temperature, we increase the pressure. Okay, all right, now let's see, we're going 17 minutes. I think that is a very good spot to start. Stop with this first video, and that's video number 1 of our terminology, and in the next one we go into the one that's going to lead us to our first problem of the course. Are you excited? I'm so excited, I can't wait.